actually really awesome. It mostly covers kind of like how to use fuzzing to find vulnerabilities in applications, and then actually, you know, like once you get the results back from it, how do you know how long to run your fuzzing and what to do with the actual information you get back from it, and how to really get video covered and stuff like that. So, really awesome talk we gave yesterday.
Can I use that outlet under you?
And we'll get you guys on the way. Thanks. Here's Charles Love.
Thank you.
Thank you for the introduction. That's pretty much exactly what I want to cover today. Like you said, I gave a longer talk yesterday, and I have a look at files and programs and stuff that goes along with this talk, and I'm going to put those on my OpenRC account probably tomorrow or something. So if you want those files and you can't find them, just send me an email and I'll set you up with them. Okay, so what am I going to talk about? First, I'm going to spend a couple minutes just making sure everyone's on the same page about the terms I'm going to use for fuzzing and what fuzzing is all about. Then I'm going to talk about a lot of the problems that you'll run into when you try to do fuzzing. And then I'm going to move on to code coverage, which is kind of what it talks about, which is something that I'm going to show you can use to sort of answer a lot of the questions that you'll run into when you're trying to fuzz something. Then I'll do a bunch of examples, and then I'll talk about how you can make your code coverage. So, if I had like 5 minutes to describe to you what fuzzing is, and I actually have less than that, this is what it is. So basically what fuzzing is something that QA teams and testing people have been doing for 10, 15 years, and security folks just in the last few years have realized what a great tool it is. And what it is basically inputs into a program, which we'll call test cases. You send those into a program, lots and lots of them, and you make little changes to them, and you watch the program to see if something bad happens. That's basically all fuzzing is. It's just, how do you make the inputs, and how do you monitor the program, and how do you do it better? But, the 3-bullet slide is, you send a lot of inputs into a program, you make malicious changes to them, and you monitor the program to involve them. And so here's basically the simplest example I can think of fuzzing. So, on the top line there is a valid HTTP GET request. And underneath there are just some changes I made to it, so I've added anomalies. So the first thing I did was I replaced the verb get with what it is. Add some slashes, add some %ends, whatever I could think of, I did. And the point, one thing to take away from this is that, well, how did I decide to make those changes? Well, I could have made lots of changes, and obviously I could have made infinitely many things there, right? And so the question is, how do I make these inputs that are in a smart way? And how do I know, how do I know how many to make? These are the questions that you might not think of right away. Okay, so anyway, let me explain some more fuzzing terminology and different ways that fuzzers work. So there's basically 3 classes of fuzzers. The first is called mutation-based, second is generation-based, and the third is evolutionary. And I'll talk about all 3 of those real quick. So mutation-based fuzzers, they're called dumb fuzzers, and it's basically because the structure of the inputs to the program, like the test cases, you don't need to know anything about that. The fuzzer just blindly takes inputs, changes them, and gives them to the program. So you start with a valid input. So this is that HTTP example I just showed you. That was an example of mutation-based. So I started with a valid get, and I just started tweaking it. So the anomalies you add, they can just be random. So like, I add a bunch of A's. I could start flipping this, whatever I want to do. Or they could follow some sort of heuristic. So, obviously adding a lot of A's, there's like a reason for that. I was hoping maybe to find a buffer. I added some %ends, and there's a reason for that. I was hoping to find a format string buffer. So the changes you make can have a reason, or they can just be random. Basically, it requires no time to set up. And in my talk yesterday, I did some buzzing, and it basically took me 30 seconds to get it going. Because I don't know anything about it. All I need to do is have some program that can arbitrarily take an input, make random changes to it, and send it to a program. It's really easy. You have to be very careful, though, with this type of fuzzing on any protocols that have checksums or challenge responses or protocol IDs or anything like that. Because since the fuzzer doesn't understand anything about the protocol, it's not going to know how to fix up those checksums. So the program probably, if there's checksums, first thing it's going to do is check the checksum. If it's not valid, it's going to kick it out. So your fuzzer's just going to be testing like the first 5 lines of code. It's not going to be testing very much. And then I give some examples of some fuzzers that are of this type. And the next type is called generation-based, and they're called generation-based because you generate the test cases from scratch. So if you notice, if back to the HTTP example I gave on the second slide, if that was me really trying to fuzz Apache or IIS, I'm only going to be fuzzing the functionality of that process gets, right? So there's obviously way more HTTP verbs like if you do head or trace or whatever. So there's a lot of other things that I'm not fuzzing because I just took one input and I started changing it. So with generation-based, you don't have that problem. You start by reading the documentation, whatever you can find, RFC, and you build up inputs from scratch. So in this case, if I was really going to fuzz Apache, I was going to use a generation-based approach. I'd read the HTTP RFC, and I would figure out all the verbs. I would write responses or write requests that are tokenized exactly like the RFC explains. So usually at the bottom of the RFCs, there's some ENF type grammar that will explain how the request will go. But anyway, the point is you build it up from scratch. So in theory, you should have every kind of test case that the program with whatever it accepts. So you would think that you'll do better with this. And the downside is it takes a long time to set up. So, like I said, yesterday I started a fuzzer. It took me like a minute to get it going. If I wanted to do a generation-based approach, it would probably take me like 2 weeks, a month, I don't know. You basically have to read an RFC and write down in a programmatic way how every type of input could possibly look. And obviously that's going to take a very long time. There's some examples of some fuzzers that are set up to do that. And the last two, they're commercial. And their basic business model is let us do that work that took a month and describe all the test cases, and we'll give those to you. The final type of fuzzing that I'm going to talk about, at least, is called evolutionary. And basically, so these three types of fuzzing I'm talking about are all differentiated on how you get the test cases. The first one was you take inputs and you change them. The second one is you build them up from scratch, and this one is you somehow generate new test cases from watching how the program behaves. And Autodapt was the first one that did that, and it basically prioritizes test cases based on whether they hit these dangerous APIs. So if there's obviously either a very, very large number of test cases or maybe an infinite number of test cases. And if you see some that are hitting some string copies or something like that, they prioritize those. The second one, and I'll talk about this one later, is called EFS. And it basically tries to get new test cases that are going to get better code coverage than the previous test cases. Like I say here, this is still like super early, and it's really hard to use this. Autodapt is like very mature, but EFS is still very, very new and very difficult. Alright, so you downloaded a fuzzer, you read a paper about fuzzing, maybe you read the book on fuzzing, and you're ready to do it, right? And you sit down, you figure you know everything there is to know, right? I explained that first slide to you, what else is there? Well, as soon as you sit down and you try to run these things, you're going to run into some problems. And these are some of the problems you're going to run into that no one's basically told you about. The first is, like you saw in the HTTP one, mutation-based fuzzers generally have an infinite number of test cases that you can set. So the question is, if I can set infinitely many of these, I obviously can't set them all. So when do I stop? Do I stop after an hour, a day, a week? So the question is, how do you figure out when to turn off your fuzzer if it has a bug? Obviously, it's unanswerable in general, but you can actually make some sort of smart decisions. The second one, generation-based fuzzers, they generally generate a finite number of test cases, but still, what happens if maybe it's a million test cases, you run them all, and you haven't found a bug? Are you done? You just go home, or can you do something smart? The third one, how do you monitor the target application? So I told you you're supposed to send inputs in and then watch to see if something bad happens. Well, typically what people do is they attach a debugger to it, and they wait for it to throw an exception. Well, there's lots of things that a program can do that's bad that doesn't have anything to do with exceptions. So you can imagine like SQL injection, command injection, how about, what else can go wrong? You get like a directory transversal. So there's lots of things that go wrong in programs all the time that have nothing to do with it, just falling on space. And the question is, how do you monitor for those types of events? What happens if you find too many bugs? So that sounds kind of funny, but it can happen. So what happens if you've got, every time you send a test case, the program dies, but it always dies in the same spot, and that spot's fully uninteresting. What do you do then? And you'll see that a lot in programs that are not very well written. But still, it makes it where you can't use fuzzing. So say I've sent in 1 million test cases. How do I figure, and the program crashed at some point. When I went to bed, I woke up the next morning and I saw that it died. How do I figure out which test case crashed? Or test cases. Maybe it was a series of test cases. And then past that, suppose I figure out it was this test case crashed the server. How do I take that information and figure out exactly what went wrong inside the server? Finally, when you're done fuzzing, how do you know how good a job you did? So maybe I fuzzed something, and maybe some guy off the street set up a fuzzer and ran, and neither of us found a bug. Did I do a better job than him or not? I hope so, but maybe not. Finally, when do you just give up? When have you fuzzed and you've done basically all you can? All right, so here's an example of one of these problems in action. So I have a PDF file and it has 250,000 bytes in it, and these are one of the files you can get off of the OpenRC site tomorrow. So it turns out that out of all those bytes, there's one byte out of it that if you change to certain values, it'll cause Acrobat to crash. And you can't even change it to just any byte. There's just certain bytes that this one byte can be changed to, certain values that this one byte can be changed to that'll make it crash. And it's not at the beginning either, it's actually towards the end of the file that this byte exists. So if you do the math, you figure out that there's that very, very low probability of any particular test case finding this bug. And so if you do some more math, and you figure out, basically on average, you're going to have to send in 127,000 test cases before you'll find this guy. And if you use FileFuzz, for example, which generally sends test cases into a second, that's basically 3 days. So the question is, if you ran a fuzzer and you just turned it on, it didn't find a bug, you wake up, it's day 2, you come back, it's day 3, it still hasn't found a bug. Are you really going to let the thing keep running, or are you going to turn it off at some point? And that 3 days is just an average. Sometimes it might have taken you a week before you find the first bug. I fuzz all the time, and I've never let a fuzzer run more than a day. Maybe that's because I'm not so smart. Okay, so this is another example. 3G2 is a video file format. And I didn't update my slide, but it turned out when I wrote these slides 2 weeks ago, this was true. I have a particular 3G2 file, there's nothing special about it. Turns out if you go through and you start changing each byte to an FI, that QuickTime Player will actually crash 42% of the time. So it's impossible to fuzz QuickTime Player for this file format, because the thing always dies, and it always dies in the same boring spot. The fact that it dies there makes you think, well, this program isn't written very well, so there's probably other bugs. But you can't test for those. It turns out since 2 weeks ago, between now and I tried to rerun a couple days ago, they fixed this bug. So they silently fixed this guy. But if you don't patch your QuickTime, you'll find this behavior. Alright, so those are some of the problems that when you really try to sit down and do real fuzzing, that you're going to run into. Some of those problems are open research problems, and no one really knows the answer. Some of them I kind of have an idea what to do, but I don't have time to tell you. So just bug me afterwards. And some of them, I claim you can use this concept of code coverage to answer. So what's code coverage? It's basically a tool you can use to figure out how much code in your program has been executed. You can do it for source code or for binaries, although everything you read, except at hacker conferences, is going to say have the source code, because most people do. So there's different kinds of code coverage. I'm going to explain real quick a few of the different kinds. So there's line coverage, which measures how many lines of source code or assembly you've executed. Branch coverage, which monitors how many branches in a program you've taken. So there's a little code sample there, and if you think about it, so you can cover each of those lines with just one test case, if X is 3, because you do that and you do the conditional there. And then if you want to do each branch, so there's 2 branches in that program, it actually takes 2 test cases. So you can see that if you cover a branch, if you look at branch coverage, it's a finer grained metric than line coverage. So you get more information. And then after that, there's an even finer grained metric called path coverage. And what that does is it measures all the paths of the program and how many of those you've actually executed. And so there's another piece of code, and if you think about that for a minute, you'll see you can get all those lines covered in just one test case. But there's obviously a lot going on in the code, so that doesn't give you a good idea of what you've done. you can cover all the branches in 2 test cases, and you can figure out what that is. And then it actually takes 4 test cases to go down each path. So that just shows you how you can how much of a better measure of path coverage is. However, it turns out path coverage, like, no one uses it because there's too much information. So if you think about it, and if you think about this last slide, it makes sense. But normally, for path coverage, if you go down, if there's n branches in a program, and it'll generally take 2 to the n in test cases to go down all the branches, but it'll take 2 times n to go down all the branches, and 2 to the n to go down all the paths. And if you think about how many branches are in a program, like SendMail, well, there's a lot. So you can't go down all the paths, it's impossible. So people don't even try to measure that. And if you start thinking about loops, it's even worse. So obviously you could have infinitely many loops. There's people have ways around that, but still, it's basically not a good approach. And another problem is there's this thing about infeasible paths. So there's a little code sample, and if you just sort of look at it from a mile away, you're like, oh yeah, 4 paths. And if you had like an analysis tool, it would probably tell you there were 4 paths. But if you think about it for a second, one of those paths can't happen. It's impossible. And so that's something you have to worry about. Alright, so those are different kinds of code coverage. My favorite is line coverage, just because it's easiest, but people choose different things. And there's actually more than these 3. So I claim that this code coverage thing is going to answer a lot of your questions about fuzzing. So let me tell you how you get it. We've got source code, it's real easy. When you compile it, you just do something tricky, and it adds some extra code, and which reports your code coverage. If you don't have code coverage, or if you don't have source code, you have to do something different. There's a few approaches you can take. One is you attach a debugger to the thing, and you just monitor what it's doing. And that's basically what PyMay does, and I'm going to show you that later. Another idea is you can do something with virtualization. So you could use like Valgrind. I call it Valgrind. I guess the proper terminology is Valgrind. Anyway, there's actually something in there that'll almost do it already out of the box. A little bit of changes would definitely do it. Or you could use like a real virtual machine like Box%. And finally, you could do what compilers that add in the code coverage stuff do by adding instrumentation. You can do that dynamically in binaries too. I've never done that though. Alright, so I'm going to preach to you for like the next half hour about how great code coverage is. But before I start, let me tell you about how it's not as great as I'm going to tell you. So basically, there's some problems with code coverage, and this is what they are. The main thing is, and you'll hear people complain about this all the time, that code, just because code's covered doesn't necessarily mean it's been tested or fuzzed or whatever you want to say. And that's absolutely true. So this is an example here, and you can imagine hitting this string copy, and it can be covered, and so you're like, oh, it's covered, it must be safe. But obviously it's not. If you send in a large source, there's a problem. Maybe you covered it with a small source. And all it would have taken is a little change, and you would have crashed it. So just because code's covered doesn't necessarily tell you that it's been tested well. Another thing that happens is there's going to be a lot of code in a program that isn't covered, but you don't particularly care about it. So there's another little sample code, and basically it's out of your control whether this malloc fails. And there's going to be all this code that's never executed and is run out of memory function. But then again, you don't particularly care about that because it's not really under your control. There's going to be a ton of code that you don't really care about, but you may or may not be covering. And which leads you to this idea of attack surface. So the attack surface is the portion of the code that you can actually get executed from either the remote access point that you're looking at, or you're reading a file, or you're mailing arguments, or whatever you're monitoring. So wherever the attack is coming in, whatever code you can get executed from that is called the attack surface. And so when a daemon starts up, it has to bind to a port, it has to read its configuration file, it has to do a bunch of startup stuff, and that has nothing to do with you attacking it. And so there's going to be some code that's executed, some code that's not. You don't really care about that because you can't control it. What you really care about is the part that processes your data. And the problem with that is that since you can't, there's no way to really measure the amount of code that is the attack surface. And so when you run your code coverage tool and you say, hey, I covered 17% of the code, it doesn't really tell you anything because you don't know how big the attack surface was. Maybe you covered every line that was humanly possible. Or maybe you could have covered 90% of the code. You have no idea. So basically the fact that there's this attack surface means that absolute code coverage numbers are meaningless. All that it's useful is if I cover 70% and you cover 20%, you did a better job. That's all I can tell you. But we can't say anything about, if we're done, if we've covered everything we can cover. So now the examples, which that was in the title, so I definitely have to do some examples. I'm going to start with some source code examples, and just because I think it's a little easier to understand, but then we'll quickly move into assuming you have the binaries and stuff. That's normally what we have in real life. Okay. So, like in the introduction, I found a bug in the iPhone, and there was like a lot of press about it and stuff, but when it was going on, I'm such a responsible guy, I couldn't tell anybody about the bug. And so I couldn't tell anyone how I found the bug, which I think is really interesting. And in my Black Hat talk, I didn't have to. So basically, I never told anyone how I found the bug, but how I found it was with Fuzzing and code coverage. So code coverage is really what helped me find the iPhone bug. So how did I do it? It turns out that there's this WebKit, which is an open source project that all the Apple internet applications use. So like the mail tool, the web browser, the dashboard, everything uses this WebKit. Actually, some others like Nokia phones or something uses too. Anyway, lots of things use it, and it's open source. You can check it out. That's good. If you surf around on the WebKit website a little bit, you'll see this little thing. It basically says that, hey, it's open source, please contribute code, and by the way, if you're going to contribute code to the JavaScript core code, make sure that you run this test. Oh, that's cool. So now I know what test we need, right? So I can figure out what code they're testing and what code they're not testing. So let's do that. So the tool that I use to look at the code coverage for WebKit is called Alcove. So it's open source. It was originally made to look at code coverage of Linux kernels, but it works on anything. And the cool thing about it is, unlike Gcov, which most people have probably heard of, it'll compile everything into one file and it'll make a little HTML report. So it's nice to use, but it's actually sort of a pain. It's a pain to use, but it's nice. So here's how you do it if you ever want to try it. So to build it, you run the script that comes with WebKit with a nice coverage flag, which does everything for you. Run the test suite, and then Alcove falls on itself. So you have to do a lot of things to make it happen. You can figure those out if you ever tried. Then you run this Alcove command, which gets all the code coverage from the test suite that you ran. Then you generate this HTML report with this other Alcove tool called GenHTML. And this is what you get. Hopefully you can read it from where you are. You see my mouse? Okay. So if you look, these are all the directories in the JavaScript core part of the WebKit. If you look over here, you can see how many lines of code are in each directory. So basically, these two directories right here are the ones that have the most code. And if you look, there's one directory. So if you look up here first, the entire project has 60% code coverage. Like I said, that's sort of meaningless. We don't know if that should be 100 or if that's great. But relatively speaking, we can look at these two directories and know that 80% of this directory is covered, and only 55% of this directory is covered. So obviously they did a lot better job testing this code than that code. So just saying that again, 60% of all the lines are covered, 53% of all the code is 80% covered, and 17% of the code is only 55% covered. It turns out that 70% is in the Perl-compatible regular expression code, PCRE. So it was covered way less. I said, hey, let's take a look at that. And I was also sort of excited because, regular expressions are complicated and they need to parse, so it seemed like a good place to look. So we wrote, it was myself and two other guys, we wrote a 20-line Perl script that generated random regular expressions. We ran through the PCRE parser. We just ripped it out of WebKit. Ran it, and it didn't crash. We ran it for a few hours or something. It didn't crash, but we saw all these errors that said something about internal error code overflow. And so we looked in the source code to see what that was. It turns out, like the line before that, it totally just blindly copied some huge buffer, and it really hurt itself badly, and then it told us about it, which was nice. So this was good. We found a heap overflow, and that was sort of that's how we found the bug. Then the question is, okay, we want to write an exploit for it, and all we know is that with a particular regular expression, we can cause it to overflow by 2 bytes, a particular heap buffer. And if we put more of those particular regular expressions into a bigger regular expression, we can overflow, more of these 2 bytes. That's all we know. And we got our shiny iPhone. We know it's vulnerable because if you start to a web page, it'll crash the little browser in the iPhone. But we don't have a debugger. We don't have any way to compile code for it. We don't have any way to run code on the iPhone. Now you can do all that stuff, but at the time you couldn't. All we have are crash reports, which are basically like little Dr. Watson things. And we had 4 dumps after we tweaked things a little bit. So the question is, well, how are you gonna write an exploit for this, right? It's tough. And so all I do all day is sit around fuzzing. So it occurred to me, all we need really is to get control. So we need the program counter because it's like a little embedded ARM device, and we need to just point to our shellcode, right? So if we can do those 2 things, we're done. Not rocket science there. I do that without a debugger. Well, the same way that I build all my clients while I'm watching TV, I do fuzzing. Alright, so don't tell my clients that. So what did we do? We wanted to try to fuzz the thing and let that find the exploit for us. So this bracket bracket star star bracket bracket is the evil regular expression that would overflow a heap buffer by 2 bytes. So all we did was we generated hundreds of regular expressions just randomly, and we sprinkled in these little evil strings into it. Kept launching the iPhone over and over and over against these these bad JavaScript regular expressions. And then of course it crashed a lot. Sometimes it didn't. And we gathered the crash reports. We looked through them and found a good one. 99% of them were just didn't seem important, but eventually we found one that looked good. And this is what it looked like. So here's the program counter. If you disassemble it around there, it looks like it's unlinking some sort of linked list. If you look at the registers that are involved, they look controllable. It turns out they are. So what's that mean? Well, it's just very typical. You control the things in an unlinkable linked list. That means you can write 4 bytes anywhere. So what did I overwrite? What sort of data structure was this? Was it heap metadata? Was it some WebKit specific structure I've overwritten? I don't know what it was. I just know it works. And that's the beauty of fuzzing, and that's the beauty of this exploit. I have no idea how it works. So I was able to, so I can write 4 bytes anywhere at this point. The question then is, well, what do I overwrite? And I could figure out something more clever, but I know for a fact that there's going to be addresses on the stack that eventually is going to stick into PC. And so if I could overwrite one of those, that'd be good. With the debugger, I'd be done, but I don't have a debugger. So I need to figure out where on the stack I'm going to overwrite. Luckily, the stack doesn't change in memory, so that's convenient. So what I did was I just fuzzed them. I fuzzed again. So, and like I said, it's technically not brute forcing at this point, but I like brute fuzz. So all I did was I started the stack pointer, and I just started moving down the stack and overwriting things and getting the crash reports and seeing what would happen. Eventually, I found this one, which shows that the program counter is actually executing on the stack now. So I've actually overwritten a return address with the stack value, and then it returned to that and started executing, and then eventually got a bad instruction. So I got control. And again, I don't particularly know why, but it works. So when I say when I don't know why, obviously I kind of know why, but maybe this might not have even been the first value on the stack I could have overwritten. It might be, it might have had to return 5 times before I got to this value. Or it might not have ever even been a return address. It might have been a function pointer on the stack. I don't know. But all I know is I had control. And then this morning I'm on East Coast time, so I was up at like the crack of dawn today, and I just started looking up. And I came across this on the Apple page. So I gotta give some credit. At least they're trying to make things more secure. So they want to hire an iPhone security engineer. If you're interested, you can apply to that job. So it's like Captain of the Titanic. I would take it. So that's the first example. The next example I want to talk to you guys about is libpng. So PNG is a file format. I all know that. libpng is used in most open source things to parse PNGs. Not surprisingly. And so I want to fuzz it, hopefully find a bug, and if not, answer some of these questions about when to turn off the fuzzer and so forth. So the first thing I want to do is build it. So I'm assuming I have source code at this point. Build it so that it gives me code coverage information. So I do these steps. And the important thing is to look at these. You have to give special flags to the GCC, so it'll build its code coverage information. The make dies out because you can't really do this code coverage stuff with dynamic libraries. So you have to build it statically. So that big line in the middle of me building the thing statically. And the result is I get this rpng-x, which is this trivial little viewer that comes with PNG that will actually display PNGs. And that's about it. Which is perfect for us. Alright, so now I want to fuzz it. So I'm gonna do dumb fuzzing because it's easier. And for that I need a valid PNG to start with, and then I'm gonna start changing. So what else do you do? I Google for PNG, and the first thing I come across is this PNG on the internet. I get file cub set up, and then I want to start fuzzing it. This is a file you'll be able to get in a couple days from me. It's just a little like 20-line maybe C program that fuzzes files. It's like totally trivial, but it finds so many bugs you won't believe. It takes 1 to 17 bytes in a file and makes changes to them. So it takes 1 to 17 bytes and changes it to a random value in a file, and it just generates, and then it prints out a new file like that, and it does this 8,000 times. So create 8,000 files that have 1 to 17 bytes that can change. That's it. The ultimate in dumb fuzzer technology. And I'm giving that to you for free. Nice. You're welcome. So then I have an even better tool that I'm going to give you too, called script.sh. So it's an even more sophisticated language called bash. What it does is it launches programs and then lets them run for a little bit and then kills them, and that's it. So, and the other thing I want to point out is normally, like I said, what you want to do is you want to attach a debugger to your program you're running to make sure you know when it dies. If you're doing it on a Mac, you get that for free. So Apple has this cool program called Crash Reporter that monitors all your programs, and when they die, it tells you about it. So you can fuzz on a Mac and you don't have to worry about it. It'll tell you when things crash. So that's why I always fuzz on Mac. Okay, so I took that file I got off the internet, I ran these two little trivial tools, got 8,000 files, and I started running them into this program. Here's the steps I followed to get my code coverage. It turned out I got 10.7% of lines covered, source code lines. Well, how's that compared to other things? Well, I would have only gotten 0.4% if I just got the usage statement. And then if I just opened the clean file, the real legitimate PNG, I get 10.1%. So all that it took me like a few hours to do that, and I only got 43 more lines for all that. So what does that mean? Well, it can mean a lot of things. One thing is, I don't know what the attack surface size is, so maybe 10.7% is good. Maybe I could only get 11%. I doubt it. That's probably not the case. Maybe, well, it is true though that this libpng does do, it writes PNGs as well, read PNGs, so there's some code you're not going to hit, but, probably not. Maybe I chose a bad file. I just chose that thing off the internet. Maybe it matters what file you start with. I don't know. No one really talks about these kind of things in Fuzzing, which is kind of why I want to do this talk. So to test my theory that maybe I chose a bad file, I grabbed some more files off the internet. So 4 more. I did the exact same thing. I fuzzed them all individually, and I got the code coverage from them. This is what I found. So the first file is over there we already looked at, and it turns out it makes a huge difference which file you choose. So some of those files, got much better code coverage than the one I had. I did the exact same thing. So what does that mean? Well, for one thing, the initial file can make a big difference when you're fuzzing. I got 50% more code coverage from one than the other. And that doesn't necessarily mean I would have found 50% more bugs. But what it does mean is that the code that I didn't cover from the first case, I definitely would have never found any bugs in that code. Well, that was fine. I found 5 files. I ran them each individually. What would have happened if I ran all 5, basically at once? It turns out I would have done even better. So running all 5 together was even better than running even the best one by itself. So I got up to like 17% code coverage. So what's going on? Well, basically what's going on is each PNG has certain elements in it that have to be parsed by the library. And almost all these are optional. So some PNGs are going to have certain elements in them, and some of them aren't. So what happens is when you get different PNGs, they're going to have some elements in them, and it's going to require some code processing. If you fuzz a lot of different PNGs, there's going to be a better chance that any random little element is going to show up in that collection of PNGs. So I named this after myself. I was so proud of it. It's called Charlie's heuristic. You must always use that word for it from now on. What you do when you're fuzzing with dumb fuzzing is you keep adding files to your collection until the cumulative effect doesn't get you anything extra. So I'm hoping to copyright that, write a book, I don't know. But something I just thought of. So basically, this is something that with code coverage, so before this, people say, I don't even know if people would say you need to fuzz a lot of different files. But it turns out it's true, right? And not only now do we know, thanks to code coverage, that you need to start with a lot of different initial inputs, it also tells you when you've chosen enough initial inputs. So, that's really valuable. The fact is, though, that no matter how many PNGs you collect on the internet, you're probably never going to find some PNGs that have the most obscure little elements in your process. So the PNG is set up to process basically any PNG possible. And people just don't write PNGs, programs don't write PNGs that can do anything. So enter generation-based fuzzers. So if you read the RFC, though, you know every single chunk. I'm cheating a little bit. I read the RFC. If you read the RFC, you know every single type of element that can possibly occur inside of PNG. So you can write images that have every single element possible. So in theory, you should be able to test more code that way, and you should do better. And in fact, that's the case. In order to do that, though, it takes a lot of effort because you have to read the RFC, understand it, write code that will generate all these PNGs with all the different elements. And this is basically the kind of work you have to do. So I use Spike, which is a generation-based fuzzer. It's been around for a while, by Dave Vitale. And this is basically what it kind of looks like. So you have to go through and tell every byte what it is, can you fuzz it, and but you can generate all these files, and I did it. And again, that'll be available for you if you want. And you can see generation-based fuzzer did do much better. So you got almost 25% of code coverage that way, compared to when we started, we were only at 10%. And again, code coverage doesn't necessarily mean you've done well testing, but certainly you've done better, right? Okay, so basically I use code coverage to measure how much better I would have done using generation-based fuzzer than mutation-based fuzzer. Okay, but you run into this problem again. So this is like an obsession. When do I turn off my fuzzer? Because I fuzz a lot and I don't know when to turn it off. That's why I think about it. So during all this testing for all these slides, what I do, I use mutation and generation-based fuzzers. I generate over 200,000 of these PNGs and ran them in the program. It never crashed once. I like to think I know kind of what I'm doing, so you wouldn't think that I missed something too obvious, but it's like it didn't crash. So what happens? Well, it turns out this is fully common. If you're fuzzing something that's really good, which is what I like to focus on, it's usually it doesn't crash. You're going to fuzz Apache, and you set your buzzer against it. Don't expect to come back in 5 minutes and have it fall over. It's not going to happen. So the question is, what do you do now? And the answer is code coverage. So basically, I've shown you some cool stuff you can do with code coverage. What I want to show you now is the most important thing. Is the bottom line is how many bugs you found. So this is going to tell you how you can find more bugs using code coverage. Because I didn't know. I've never told you guys what a PNG looks like. The question is, could you figure out how to take your initial PNG that got you 10% and do better? Just not knowing anything about PNG, just looking at code coverage. And the answer is yeah. So here's what the outcome report looks like, and if you can read it, it's basically a bunch of if this, if this, if this, if this, and you can just look and see exactly what it's looking for, and you can add that to your PNG, and then you can get better code coverage. So there's all these functions that have never been tested with your fuzzing, but you can easily make it good. So you can imagine getting better code coverage, or you can imagine doing better testing by looking at your code coverage from your current testing. So basically, the algorithm is you find spots which weren't covered, you generate new test cases that then cover this. And again, for the 10th time, the thing to take away from this is not necessarily that code coverage will find bugs, but that code that hasn't been covered, you've definitely not tested, you won't find any bugs in that code. So let me tell you real quick how you can get code coverage from binaries, because that's basically what we care about, and a lot of you guys care about hardware, which is even like the next hardware level, which I won't get into. But so you have a binary, you want to fuzz it, you want to get code coverage. What do you use? You use PyMay. So PyMay is this super cool reverse engineering framework in my bedroom, And what it does is it integrates a debugger, information from InterPro, cracking software, and a database. It allows you the ability to basically script and do things that a reverse engineer would want to do very quickly and easily. It has a module called pstalker, which basically gives you code coverage, which is what I care about a lot. So the way it works is you put your program into InterPro, you export the information into this PIDO file, which is something that it uses, which basically tells Pyme where all the basic blocks and all the functions are. What Pyme does is it attaches to the binary, it sets breakpoints at every single basic block, and it waits to see what happens. As you execute the program, when it hits these breakpoints, it records it, and then it knows where you've been, so it knows the code coverage. And this is your screenshot. You can download it, it's open source. It's written in Python. One minor issue is that before I kept launching the PNG viewer over and over and over. You can't do that with Pyme. You want the thing to be running all the time. That's an easy fix. You just have it, you put it in a browser, point the browser at a web server that just keeps refreshing the different image each time. And there's the code that will do that. Okay, so you might not be able to see that so well, but it's the equivalent of that slide that showed, all the lines in that if else that you missed. Here it is if you look at your Pyme. And again, you see the same phenomenon. You see the green squares that you hit and the white squares you missed. And you can see they're like, all over the place. So it'd be really easy to go in there and figure out exactly how to make your PNG better. And that's without knowing anything about PNG. So like maybe PNG is in the future it becomes a proprietary protocol. And so you don't know anything about it. But you can still figure out exactly how to make changes to your files to get better. So let's do the same exact thing I did before, except we'll only use binary. So take Safari, load it into Pyme, and I guess what I want to say here, let me go back. So if I show you this slide, it's pretty easy to understand. Hey, yeah, I know what you're doing. I know how to make changes to it. But the question is, hey, how'd you find this? The binary is huge. How did you get to this one particular spot where it was obvious? And the answer is Pyme will do that for you too. So what you do is you put Pyme against Safari, you browse a bunch of sites, try to avoid the ones that have PNGs because that's what we care about. It turns out porn sites don't have a lot of PNG images, so you're pretty good to go. And what happens, you just keep going and going and going until there's no more breakpoints. Which means you've executed and recorded a lot of code that has nothing to do with PNGs. Okay, then you save that, and you do it again, except this time you only look at stuff that has a lot of PNGs on it. And you record what you get there. If I film turn out the first run from the second run, you're left with only the code that has to do with PNGs. And you very quickly zoom right in on that code I showed you. So what happens? Well, in this particular deal on Safari, there were 123,000 basic blocks. When I was just surfing, it was 12,000 of them got hit. When I was looking only at PNGs, it was only 1,000. So I already narrowed my search time to only 1,000 basic blocks. And by looking at those, you can very quickly, so it's only less than 1% of the total basic blocks I'm able to look at, and I'll quickly find that spot in the code I showed you. And these yellow ones are the ones that show up just when I was surfing. Okay, so what's the only drawback with Pyme? Well, Pyme works from InterPro, so if InterPro messes up, Pyme messes up. If you're trying to get code coverage for some binary that has anti-debugging stuff built into it, you're probably going to have problems because Pyme is essentially a debugger. You kind of have to know what DLL you're interested in, or you have to load them all, which is like a pain. So it's sort of a chicken and egg a little bit, but if you're in the worst case, you just load everything and it just takes a little longer. And in this case, I had to set 123,000 breakpoints, and anyone who saw my lecture yesterday knows that takes like 10 minutes. So it may take a while. All right, so I showed you like how you can imagine getting better code coverage. Now I'll show you how you actually do it. Basically 3 ways: manually, dynamically, or from the binary. So I kind of explained manually how you do it. This is just a zoom in on that other slide. And you can see right here, well, there's a jump that I didn't take. And, trace back to compare. Oh, look, there was a byte. I should have said the PLTE, and then that would have been in business. So let me show you one more example. So FreeCiv, this is like, fun multiplayer game. And like I said, don't ever run it on any computer that you actually care about because binary, put it in IDAPRO, get the PETA file, launch the program, attach it to time A. If you want, you can filter out what happens just with like boring netcatting to it, but that's not even necessary. And then you start fuzzing. Time A will tell you when you hit. To fuzz it, I use the tool called GPF, written by Jared DeMont. It's a good little fuzzer. It's a mutation-based fuzzer. Works on PCAP captures. So you fuzz FreeSib. That's the lines you want to do it. What's the problem? The first problem we run into is if you try to connect to FreeSib more than like 3 times in a minute, it doesn't know what to do. So it's not like a really good program to fuzz. So I had to build in like all these sleeps to the GPF. It took a lot longer to fuzz. I went to bed, woke up the next morning. I had 96 functions during my fuzzes. I looked back in IDAPRO to see if I could do better. I found this humongous switch statement. And I only hit one switch. So I know I can do better, right? I traced it back to see where that data came from. It turned out it was the 3rd byte in my packet controls that gigantic switch. I said, okay, I know what to do. At this point, I was basically just sending more or less random data. I figured out the 3rd byte's important, so I'll make sure that GPF modifies that 3rd byte a lot while I was doing it. So I've taken what used to be random by using code coverage. I figured out a little bit of the structure of the packet, and I'm going to use that to my advantage. So there's another GPF line you can run. Now I got better coverage. The first time when it was more or less random stuff, I got 614 lines, or basic blocks covered. This time I got 2,300 basic blocks, so I did much better. And I did hit every case in that switch statement. Still, I didn't find any bugs, right? So, code coverage is academic and cute, but if you don't find bugs, you're going to get fired. This time won't. So this is just reiterating what you do is you send random data, you look at code coverage, you figure out a little more structure, and then you send some more random data with that structure, and you keep going. Okay, so I said, okay, I know about the 3rd byte, so now I want to fuzz the rest of the packet. I do that here. I started, I started fuzzing it, and I immediately, the thing just like 100% CPU egg. So I found some sort of memory corruption bug. Not that big a deal. So then what I did was I started fixing the 3rd byte, and then fuzzing the rest, and doing the same thing over and over. Eventually, hours later, I eventually got the byte, setting the 3rd byte to 0x47, so hex 47. So it's x47 and then random stuff. And I looked at the code coverage and I saw this. Okay, well, I missed a couple basic blocks here. Has a mem copy in it that I missed, and I like mem copy, so I'll make sure I hit that next time. Heap overflow. So there's a particular packet that if you send a FreeSib server, it'll fall over on its face. So link the packet. The 3rd byte's important, 2F. The 0C got me down that other left branch. Then a length of a mem copy, any size you want, into a fixed length heap buffer, and then data. And make sure you send up data because it doesn't check that you sent too much data, but it definitely checks if you sent too little. It won't copy it. Right. So, it's bugging FreeSib, not that big of a whoop. It's fun, for your friends and stuff, but there's this thing called meta server that's kind of cute too. It tells you all the FreeSib servers in the world. So it does your targeting for you. Not that you would necessarily, hack all these FreeSib servers, but now you could. I'll finish here, and I have like 5 more minutes. Is that fine? Okay. So I sort of skipped over some of the boring parts of my job, which was I started on byte 0, and then moved to byte 1, and then 2, and eventually I got to 47 X, which is actually 47. And there's actually no guarantee I was ever going to find anything, and it was kind of boring. So there's got to be a better way. It's, as I say, time intensive, aka I was going to shoot myself. So the idea is you want to automate what I was doing. So that kind of does that, but I prefer another shared tool called PFS. So it's basically a combination of time A and genetic algorithms. And what are genetic algorithms? Well, basically it's a tool that solves optimization problems approximately. All you need to do is say what the fitness of an organism is, how 2 organisms recombine. Sexy math. And then how 1 organism can mutate itself. And if you see all those things, you throw it into a genetic algorithm and it'll spit out an approximation. So real quick example, there's a function. I'll say that two numbers combined by this concept called single point crossover, which means you write out the binary representation, randomly pick a spot, take the left half of one and the right half of another, and you get your new number. For mutation, I'm just going to flip it 10% of the time. You get, this is just a slide where you can see the numbers progressing as time moves on. If you solve this thing exactly, it's 5,000. Let's see how the genetic algorithm does. Well, you can see as time went on, it basically sort of narrowed it down to 5,000. So, yeah, it kind of works. So it's not usually good at the genetic algorithm work. Okay, so how does EFS work? Well, EFS needs, if it wants to use a genetic algorithm, it has to define those exact same things. So it needs a fitness function. How fit is, in this case, the test case. And it turns out it has to do with how many lines until it comes. Makes sense. I've told you how great coverage is, so I should totally agree with this. They choose the most fit individuals to combine them. And then, I don't know how real genetic algorithm scientists can do straight picture with that kind of stuff. So they use single point crossover for the packets or the test cases or whatever you want to call it. And the only thing that's super clever about it is Jared actually respects the tokens in the packet. So he doesn't interrupt. Like if 4 bytes are for a size, he doesn't split it right in the middle of those 4 bytes. He'll only split it on the ends. And then for mutation, he adds fuzzy heuristics. Okay, so there's a screenshot. EFS. So you run it the same way as PyMA, basically. Does it work? Well, yeah, kind of. So here's an experiment I ran. This is the preset experiment again. And if you see this top line, this is the number of lines covered by the most fit test case. So I started with some test cases. I only covered, 47 lines, and by the end, I was covering, 90 something. So I did actually, without doing anything, on test cases that were twice as effective as the previous ones. Genetic algorithms aren't perfect. EFS definitely isn't a perfect implementation of them, so it's not perfect, but it's better than sitting there and doing everything I can. I'm just going to skip this part. I'll tell you why, and then I'll skip it, but please talk to me afterwards. So the final solution is you take a binary, and obviously you can analyze the binary and figure out all the different code paths just statically, and then try to figure out by hand exactly what inputs you got in that result. Right? So EFS is trying to do this approximately by saying lots of test cases and then tweak it. You got the binary sitting in front, you just look at it, right? So people have done this. Microsoft did it. At least they say they did in a paper. They don't release their tools. Catchcode, there's a tool built on Valgrind that kind of does this too. HP Gary kind of has something that does this, supposedly, but again, no one releases this tool. So what you would have to do to solve this type of problem is find where the data enters, symbolically figure out all the different paths for the program that you can possibly hit, and the dependencies in the middle that have to do with what your input was. And then these get solved. This is like the 30-second version of my talk here. So it turns out here's a little program that has 3 paths through it. Here's the constraints. So you want to define a normal program would have like 1,000 constraints. You can imagine the preset one was like height 3 equals 47, height 4 equals C, and so on. So there would have been like 6 constraints for the preset bug. And then there's this. You can use a program that would solve these constraints. So. And on that little sample, I used the program, and it found 3 test cases that really did it, 12, 0, and 4. I have no idea how it does it. It's like magic, but those really exist. And again, talk afterwards if you're interested in how it works. So using that, you can find sophisticated bugs like preset without ever. So I found that without ever running the binary. And you can also use that if you're sick of fuzzing at some point. That to you find the places that you haven't hit with fuzzing, and you can at least do stack analysis. Alright, so what's the point of the whole talk? Fuzzing sounds real easy until you try it. When you actually try it, you run into a lot of problems that no one ever told you about, but now I've told you about them, and I've told you some ways hopefully to solve them. Code coverage isn't perfect, but it's a tool you can use to try and improve your fuzzing. You definitely will not find any bugs in code that you have never executed. No one will argue with that. Increasing code coverage can be difficult and time-consuming, but there's tools coming that's going to make your life easy. And that's it.
Are your slides going to be up too?
Yeah, I'll have everything there for you. So yeah, ship some good ones. If you see me after